Hi and welcome to my channel. My name is Tobias and today we're going to look at optimization in mathematics using differential calculus. So let's have a look at example 1. We have 100 meters of fencing to enclose a rectangle and maximize the area. So down here we've got our sketch. We've got 4 sides in our rectangle, 2 sides called x and 2 sides called y. And now we need to have an expression for the perimeter and the area because we want to maximize the area. And we've got these 100 meters of fencing which we use on the perimeter. So the perimeter can be calculated as x plus y plus y. So we add all of the sides together and we get 2x plus 2y. The area is x times y, so length times width. So that's x times y. And now we've got these two expressions. We've got a constraint of 100 meters of fencing. So we put in 100 meters instead of p for our perimeter. And then we want to calculate or isolate the variable y in this expression. Or in this equation. So 100 equals 2x plus 2y. We subtract 2x from both sides. Then we have 100 minus 2x equals 2y. Then we divide by 2 to get 1y. So that's divided by 2 on both sides. So 100 minus 2x divided by 2 equals y. And then we can say 100 divided by 2, that's 50. And minus 2 times x divided by 2, that equals minus x. So we got this expression for y, 50 minus x. And now we can take this expression for y and put it onto y's place or spot in our area function. So a equals x times y. So we substitute y for this expression 50 minus x. And then we say x minus 50, multiplied by 50 and x multiplied by minus x. That equals 50x minus x squared. And now we just reverse the order of the two terms here and we get our area function, and now it's only dependent on x, so we can call it a of x equals minus x squared plus 50x. Now we want to use differential calculus to find the optimal value of x and the optimal value of our area. So we want to solve this equation called a prime of x equals 0. So that would get us our optimal solution for x. So first off we need to find a prime of x, that is this expression, so minus x2 plus 50x, the first order derivative of this expression is down here. And now we take this expression and make it equal to 0 to solve this equation up here. So minus 2x plus 50 equals 0. And we want to isolate x, so we subtract 50 from both sides. We get minus 2x equals minus 50. And now we divide by minus 2 on both sides to get our x. So 1x isolated. And that would be minus 50 divided by minus 2. Minus divided by minus equals plus. So it's just 50 divided by 2, and that equals 25. And now we want to find out, because this is our optimal solution, we want to find out if this is a maximum or minimum. So now we want to find the intervals of increase and decrease for our function. And for that we use our first order derivative. So we put in an x, a value of x that is less than 25 and that is greater than 25. So first off, the one that is less than 25. So a prime of 24 equals minus 2 times 24 plus 50. And that equals in the end 2. Then we do the same for 26, our value of x that is greater than 25. And we put it into our a prime of x function. And then we end up with minus 2. And if a prime of an x equals a positive number, then our function there would be increasing. And if we put in or get out a negative number when put into the first order derivative function here, then we know that it is decreasing. So this is our optimal solution. We know the function is first increasing, then decreasing. So that would make this x a maximum value. We have a sign chart for the derivative, so our optimal x value is 25. We just found out that it's first a positive number, then a negative number, so plus and minus, and then we could write arrow up and arrow down to give us an impression of how the function of a increases or decreases. Graphically, we can see the same, so arrow up means it's increasing until this x value 25. We can see it down here, 25. So first off, the function is increasing and then decreasing, and that makes this value of x our maximum. So this is our optimal solution for x. We have an expression for y. It's a bit up. This is our expression for y. Now we put in 25, our optimal solution for x, into this expression, and we get that y equals 50 minus 25, and that's 25. So our optimal solution for x is 25, for y is 25, and if we put this x value into our area function, then we can see that it yields us an area of 625 square meters. We can almost see it graphically also that it's just above 600 here, so that's 625. So that means that our optimal area or use of our fencing would be to make a square, because the sides of x would be 25 each and the sides of y would be 25 each. So that's 4 times 25, that's 100 meters, and that will give us a square. So a square would be the optimal rectangle if you want to maximize an area, for example, for an enclosure. So that was the first example of optimization. Thanks for watching. See you next time. Bye bye.